Let's start out by reviewing, though. We've got these reactions here. Alkane halogenation, right? Chlorination of this alkane, and then the same alkane, but with bromine and light. Now, remember, alkane halogenation involves the halogen molecules, chlorine or bromine, and light to initiate the radical reaction. Remember, chlorine is not selective, so it's going to form multiple constitutional isomers here. Yeah, it'll form that one, the primary one. It'll also form what other constitutional isomer? This one. Remember, no rearrangement. So even though these are radical carbon intermediates, they don't rearrange because that would involve filling 3 electrons into a single molecular orbital. That doesn't occur. So the framework, the carbon framework, stays in place. Unlike the carbocations, remember, we saw before. Trying to go rearrangement. Are these the only two? No, we can also halogenate on the tert-butyl thing here. And those 3 are all the same. So I think you only need to draw one there. We can also have polychlorination, but this implies just one equivalent of chlorine, but it'll give a mixture of these. And for chlorination, just draw all the possible constitutional isomers. We won't make you try to estimate what percentage or which one's major. Don't worry about that. The most stable intermediate would be the secondary one here, but you see there's only 2 hydrogens there that could be replaced, whereas here there's 9. And the relative selectivity of tertiary to secondary to primary is what, 5 to 3.8 to 1. So it's just not very selective. So draw them all out. Are these all the constitutional isomers? Yeah. Are these all the stereoisomers? Let's see, is there a stereocenter in any of these? Yeah, right here. That's a stereocenter. And it's racemic, or DL. You can draw both the R and the S if you want to there. So those would be 2 stereoisomers among, the 3 constitutional isomers. So hopefully we're clear about that. What about with bromine, though? If we do the same reaction here with bromine, we only need to draw the substituted one at the most substituted position, and that would be that secondary position, and that's the only isomeric product. Well, it's also racemic. It's also DL. That is the stereocenter here for bromination, but it's 50-50 for the R and the S. But that's the only one there. Now, the nice thing about bromination is it'll be high yield then because it's highly selective there. And then for synthetic applications, we could take potassium T-butoxide here and do what? An elimination reaction. And now we have an alkene from an alkane. It's a 2-step process, but that opens up a lot of other synthetic applications, right? We could take this and do a hydroboration reaction, for example, among many other types of reactions here. You'd want to show the borane, peroxide, and sodium hydroxide again, and that would go to give us what? The less substituted alcohol product. So going from the alkane to the alcohol, yeah, there's a synthetic thing, a few steps here. Could do a lot of other things from here, addition-wise. We could epoxidize, for example, MCPBA. And what would that give us? Give us this epoxy product, and that would give us a lot of other possibilities here. So once we have a way into alkenes, we have a lot of possibilities. There's synthetic applications from the bromide also, right? What if we treat that with sodium cyanide? This is a secondary leaving group, right? And this is a small charged nucleophile. So what are we going to get? Yeah, we're going to get the cyanide. New product there, okay? So there's a lot of other nucleophiles we could react here with that. And then from the alkene, we got a lot of possibilities as well. So you see how halogenation of alkanes takes something that's normally inert under most conditions. These don't react with all the other reagents we've looked at. The only other reaction that alkanes do is combustion, burning them to CO2 and water. That's not very synthetically useful. Yeah, we use the heat, whatever generated from that. But here with halogenation now, we put a handle on there. We now have a reactive position here in the molecule. We can eliminate it, form an alkene, which is very versatile. or do different substitution reactions there. Okay, so synthesis very important there. All right, let's get into the last couple of reactions here. Allylic halogenation. And this is going to involve alkenes again, but we're going to be halogenating those with a halogen radical here, and we're going to be getting an allylic radical intermediate, okay? And then we're going to eventually, with the reagent, get the allylic product here. But let's look at the allylic radical here. These are very stable. They're stable to the same extent of tertiary radicals, even though you might say, well, that's a primary position. Well, we've got what? We've got the ability to resonate that and delocalize over to this position. Now, that looks like it's the same thing, right? And indeed it is. But this electron here, and you have 2 electrons there. There's really 3 electrons here in this molecular orbital system. We can think of that as being delocalized like this. Sometimes we'll see a dashed line and just a radical overall. And what you should look at that is what? Draw the pi bond with the p atomic orbitals, and then the carbon on the end as also a p atomic orbital. And then you see what they all look similar, right? And what? There's an odd electron here. So you could imagine 2 here and 1 here or whatever. Or you could just say there's 3 electrons total in these 3 atomic orbitals here. We'll see in chapter 16, moving forward into 352, that these type of polyenes and being conjugated like this and resonance stabilized have special stabilization effects. And we'll look at the signs here of the atomic orbitals and see how those can mix and match and give different symmetries within the polyenes. But you could say, yeah, there's 3 pi electrons here if it's an allyl radical. And yeah, they're in this system like this. So that has special beneficial stability effects now. The conditions we're going to use here is NBS, okay? N-bromosuccinimide. And, you know, this has this structure. We've used this before, actually. Anybody remember where we saw NBS before? Yeah, the bromohydrins, when we reacted bromine and water to make a bromo alcohol way back in chapter 9, I think we'll review that. Or we could use NBS instead of bromine, Br2. This is a stable, solid material, slightly yellow. It's very easy to weigh out and beneficial that way. And we need to shine light on it to start the radical process again. Or we can use peroxide. And the standard peroxide initiator is that. No, that's not John Lennon's glasses, okay, from the Beatles. No, that's a peroxide bond, oxygen-oxygen bond, which is weak, and 2 tert-butyl groups on there. And you can only need to use a catalytic amount there for the peroxide. So that will be an initiator similar to light. So you can either show NBS light or NBS peroxide, okay? And what you'll get is the allylic bromide, okay? So this is different. It's not molecular bromine, Br2. And if we use Br2, we might think, well, we would just do the dibromide here. But you can actually use bromine in place of NBS, but you have to keep the concentration very low. If you add it in one big batch, even if you're shining light on it or have a peroxide in there, if you add Br2 directly to an alkene, you'll get the dibromide. Okay, but if you use NBS and then shine light on it here or add the peroxy catalyst, you get the alternative product now, the allylic bromide, okay, which is a different type of product. Let's look at some other reactions of this. We can also take alkenes like this, cyclohexane and NBS and light. Okay, so there's your new combination here, and that will give you the allylic bromide. Okay, and synthetically that's very useful, right? Again, we can do a lot of other reactions from this. We've got 2 functional groups we can use. So allylic halogenation is very important there. Let's see a couple other examples of this. Well, if we use this type of an alkene, again, from propene, you see the allylic radical is symmetric there. But if we use butene like this, we've got allylic radical here, and then we can trap either here or here with the bromine. So mechanistically, there's going to be a little bit of a difference here. We're going to get a mixture. We're going to get that product and which other product? You can already kind of see what it might be. If it's this allylic radical, we can either trap here or here, right? And if we trap on the end, we move the alkene over. Those are different isomeric products, right? Constitutional isomers again. This is 1-bromo 2-butene. This is what? 3-bromo 1-butene. And we'll just say it's a mix. There are ways to tell which one might be major, but for purposes of this class, just show all the possible allylic products here. Let's see, how about this one? What if we have this alkene to start with? And we do NBS. Oh, let's do peroxide this time. They really have the same effect, peroxide or light. So what are we going to get here? Well, we're going to get, let's see, the bromide right there. And we're going to get the bromide right here. Yep. Now, are those the only two products? Look, we can start this mechanistically by removing this hydrogen here, or we could remove a hydrogen here, right? What if that happens? We're going to get a different allylic radical intermediate, right? So we'd have a different product here, right? We'd have this product. And that allylic radical is symmetric. Whether we put the bromide here or over here, we'd move the double bond over, whatever. I think we get that. What about stereoisomers here? Any of these chiral? Yeah, that's the stereocenter, and that's the stereocenter. So yeah, DL, you could draw the R and S versions of both of those. So again, it's a mixture of products. Depending on conditions and temperature, you can often get one or the other. Usually it's the more substituted alkene and the bromide at the less substituted position, but I'm not going to hold you to that. This is just a mix of products that we can get at this time. Let's go to the board and look at the mechanism of allylic bromination. And it really is limited to bromine. Can't do this with chlorine. It's a special case here where, the bromine step here is endothermic. So here's homolysis of NBS to get started here. It gives the nitrogen radical, which is also resonance stabilized, by the way, and bromine radical. Bromine radical then can abstract an allylic hydrogen here, okay? And it abstracts at that position to give the stable allylic radical, okay? Now, it does get acidic. There's HBr like we saw before, okay? And then the allylic radical can abstract a bromine from NBS, but the book here is showing abstraction of the bromine atom from molecular bromine, Br2. And that's okay. It's actually known that when NBS decomposes, it will form low concentrations of molecular bromine, Br2, which is good. Because if it decomposed rapidly or formed a lot of Br2 right away, it would just add to the alkene instead via a heterolytic process, not the homolytic radical process. But again, these are propagation steps, you could say. This gives us the product. And look, this gives us bromine radical, which can then propagate over here. So the initiation here from NBS, well, you have to have a full equivalent NBS in there. But the homolysis step here from NBS is actually a catalytic thing. It can be done with light or with peroxide. And we'll get into peroxide some more and how that can work. The peroxy bond is relatively weak, and that can break readily and give you that product. Now, this allylic bromination is related to allylic oxidation or autooxidation, which happens with molecular oxygen, O2. Now, in the ground state, O2 is not a double bond. It's actually a diradical, or the triplet state of oxygen. And these are acyl triglycerides and fats. Remember, in plants, you have polyunsaturated fats where there's a double bond in the chain here, or saturated fats, which is the solid lard type materials at room temperature that are solids. Most plant oils have a lot of double bonds, particularly at this 9 position, and it's usually a cis double bond. You can imagine this radical from oxygen taking a hydrogen off there. This is a very slow process, okay? It's called autooxidation. If it occurs in the body, that can lead to carbon-free radicals, which are dangerous, okay? These can be quenched with vitamin E or vitamin C. There's natural processes of glutathione and other processes in the body biochemically that will inhibit or quench radicals. This is dangerous, though, if this carbon radical combines, you see, with more oxygen. It can make a peroxy radical here, okay? That peroxy radical can go on and abstract another hydrogen atom at an allylic position and make this peroxide alkene. Now, that's a dangerous material because that oxygen-oxygen bond is weak. You can have a migration here. If you protonate this OH, water can come off. You have a cation, eventually it could hydrolyze to an aldehyde at that spot. And that's damaging to alkenes in fats. That's the way they degrade or go rancid, okay? Causes a lot of other products to occur. But that can be inhibited by these materials here. Vitamin E, the naturally occurring vitamin that we get from our food. It's a phenol here, this OH group here. This hydrogen atom here can be a donor to that carbon radical and stop that chain process. Or we can add to food BHT, butylated hydroxytoluene, which also has this phenol OH. That hydrogen atom can be donated right here to this carbon radical. And you see if you put a hydrogen atom back on, you go back to the regular fat, okay? And you stop the autooxidation process. So, yeah, at the board, we can show you more about that if we got time, but vitamin C is similar to that has a hydrogen atom that's able to quench free radicals that way. All right, let's get into the peroxide thing here a little bit, and we're going to do that in the context of another reaction, and that's radical additions to alkenes, and we're going to do additions of HBr. We're going to be limited to bromine again, so it'll be a little more specific here. We're going to add HBr to an alkene, and we've already done that reaction actually, right? Hydrobromination, hydrochlorination of alkenes, but now we're going to do it in the presence of peroxide, okay? And it's going to be a different product. We're going to change the selectivity, okay? And we're going to get bromide at the less subject spot. We're going to get the primary bromide out. Now, if we did hydrobromination before, this is chapter 9, I think. Yeah, it was one of the H reactions. Hydrohalogenation here. If we just did it like that, what did we get? We got the more substituted bromide. And why was that? Well, we protonated, right? And by protonating, we got the secondary carbocation there. And then bromide attacked from there. And it's because of this more stable tertiary, more substitute carbocation that we get the more substituted bromide product. But now if we have the peroxide in there with HBr, look, we get a different product as major, okay? In fact, that's the only one you need to show, okay? The primary in this case for full credit on that. So let's see if we can take this alkene in with HBr and peroxide. What are we getting? You have to draw the peroxide. If you leave that off, we're going to get bromide here. But if we have peroxide here, what are we going to get? We're going to get the bromide at that spot. Now, remember, we called this Markovnikov addition in honor of that Russian chemist. This is actually the anti-Mark product now, okay? So the mechanism will have to be different here. The peroxide's doing something, obviously, and this is in chapter 15, so it'll be radical intermediate. But look, primary bromide again here for this one. Let's do a couple more here. How about this one? Again, HBr peroxide with methyl cyclohexene. So what are we going to get here? Well, we're going to get bromide, the less substituted spot. Now that'll be a mixture of isomers, cis and trans, and they're chiral. If you want to draw out all four of them, you can, but don't draw this one. Okay. If you draw this one now, you'll get points taken off. Why? Because that's the Markovnikov product. With peroxide now, it's a different mechanism. If we left off the peroxide and we're asking about hydrobromination of this alkene, this one would indeed be the product. Okay, so you have to look at the mechanism here. This is now our product for that one. Let's see, do I have another one? Oh, a couple more. How about this one with a benzene and an alkene? HBr peroxide. What do we get? We get the less substituted bromide out on the end there. Now this hydrogen goes to the more substituted spot. And I think I got one more. Oh, okay. Yeah, how about this one? HBr peroxide with this one. What are we going to get? We're going to get bromide there and hydrogen going to the more substituted. All of these are anti-Markovnikov products, okay? Different mechanism. Let's go through the mechanism here briefly. It involves peroxide as the initiator. And remember, this is a catalytic step, you can say. This only has to get things going, and it's because of the weakness of this bond. Okay, so just a little bit of heat will get that bond oscillating enough, and high enough heat, eventually it'll just come apart homolytically, and you'll create, what, 2 TB-toxy radicals. Okay? Now, the TB-toxy radical is going to shunt this pathway into what? The homolytic radical mechanism pathway. Because we have the presence of this peroxy, and that's a very reactive species, right? 7 electrons, oxygen, very reactive here for finding a hydrogen atom. So part of the initiation is actually this, where that's not going to last too long. It's going to abstract a hydrogen from this weak hydrogen bromide bond, which we have the presence there, right? So keeping track of all the electrons, what do we get? We get the stable tert-butyl alcohol, which is a byproduct here of the initiation, and we get bromine radical. And that's the key, right? Bromine radical now. Well, we're going to add that to our alkene. Now, these are the propagation steps. We have 2 initiation steps actually here, so it is a little bit different. But once we have Br dot, we're going to add that to the alkene in that way. Now, why are we doing it that way? Because that will give us what? The more substituted radical. That will give us a secondary radical. We're not going to add to the internal position with the bromine radical, because that would give us the primary radical, right? This is a secondary radical. That's the beneficial thing. Well, some of you may already be thinking and may be confused if you've read ahead. We've talked about bromine dot already from NBS when we talked about allylic bromination. And that would involve extracting a hydrogen at the allylic position. Why are we adding now here? Actually, bromine dot was adding when we talked about the allylic bromination position, but this is actually reversible, okay? This can go on and it can come back off. This is not a very stable bond, this carbon-bromine bond. But the difference now is we're in the presence of a good hydrogen atom donor, HBr. Allylic bromination with NBS, we did not have HBr. Now we have HBr with an alkene initiated with peroxide. And this, if it forms, can find what? A hydrogen source. Okay? And that's the difference between allylic bromination and HBr addition to alkenes with the radical process. So let's see, the rest of the propagation is this. We take the intermediate here and we react it with the reagent. Now this is the irreversible step. The book doesn't give you all this detail. And I think without it, these 2 reactions can be rather confusing. But now with alkene additions, okay? Indeed, this is hydrobromination of an alkene like we saw before, but it's under radical conditions, okay? And what can occur here? We've got a hydrogen source. We did not have that with allylic bromination, okay? So that helps you keep this straight. That gives us the product. There it is. And there's our hydrogen atom going on, that secondary position, the more stable radical position. So there's product. And importantly, what does this also generate? The bromine radical. We call that the chain carrier in this process, okay? The bromine radical, which we saw the halogen radical in alkane halogenation also. So these propagation steps are similar that way, but here we have an addition. We're adding to that. And once we have this step here is very fast, transferring a hydrogen atom now to that position to give us what? The anti-Markovnikov product and this guy, which is part of the propagation. So once this initiates, you see, with the peroxide, this is just off to the races now. This is a chain mechanism, right? Pulling each step along until we consume all the alkene and we consume all the HBr in this radical pathway, okay? As long as we have the initiation there. So these mechanisms are a little bit more complicated, but I think it helps explain fully why we get the anti-Markovnikov product, right? You can think of this as an electrophile if you want. It's kind of a radical cation. No, there's no charge here. But I mean, before we had always the electrophile going on the end and then the nucleophile going in this position. So in a way, we're putting the electrophilic halogen radical on the end there, okay, to give us the more stable, now radical intermediate, okay, which is similar to carbocation that we saw before. So in a way, Markovnikov and anti-Markovnikov halogenation are similar. You could argue they're the same thing. The electrophilic thing goes on the end, and whatever else goes on that internal position, okay? Whereas before our electrophile was the acid, H+, right? And then bromide, nucleophile went on. Anyway, review that mechanism, and I think you can see, what we're talking about there. It is limited to bromine. If you do it with iodide, the iodine radical addition is just too endothermic and not favorable for the first step. If you try to do chlorine HCl addition with peroxide, the second step is actually endothermic. Breaking a hydrogen chloride bond is not as favorable. So both of these steps are exothermic for bromine and highly selective for the anti-Markovnikov product. And chlorine or fluorine, like we've seen before, is just too explosive, not useful there. Anyway, let's go to the overhead here. The book has their mechanism. I like to compare what's shown in the book. Make sure we got that. So, yeah, the initiation process here is a two-step thing now. The peroxide bond is homolytically broken. Create the oxygen radicals there. And then that abstracts a hydrogen atom from HBr to give the bromine radical, and the stable now terbutyl alcohol. And you only need a catalytic amount. We're just initiating it, right? As long as we have now bromine radical, the addition can occur here now at the end position. So here they're adding on the end, the primary position, and creating a secondary radical, like we showed on the board there, yeah. And then the second propagation step is reacting with more reagent, more HBr, okay? And that is just a hydrogen atom source. And remember, we didn't have that for allylic bromination with NBS and light or peroxide. We could just react at the allylic position. But here, once bromine adds to the alkene, does an addition process, then we can transfer a proton off more HBr to give us the product, which is the primary bromide. So the discussion and everything, hopefully it's the same as the book. Hopefully I was a little more clear and thorough on the comparison between those reactions there. All right, and there it is blown up a little bit off the top here, what we've been talking about. And here's the comparison to the Markovnikov process. If this is going heterolytically without peroxide initiation, HBr, that's a what? That's an acid source. There's our electrophile, H plus, putting on the end and giving us what? The secondary carbocation. And then how do we get the Markovnikov product? Then bromide anion adds there. So compare and contrast those two mechanisms, and you'll be able to keep those straight. That shouldn't be a problem there. All right, let's get into this. Polymers, the last topic. And, you know, this is an awareness issue, I think, being aware of all these different products that we have around us in modern society. In fact, you could argue that most of the conveniences and advantages that we have as a modern society post-World War II is directly due to our ability to manipulate the chemical compounds around us, starting materials from nature, being able to convert these into all sorts of high performance materials that we take for granted really today. We're surrounded by these materials, these polymers, these fibers, these coating materials, these electronic property materials, organic LEDs now. We have all sorts of things advantage-wise that, you know, just a relatively few number of years ago, you know, society did not benefit from. So here we have polyvinyl chloride, PVC. It's not just plumbers who like PVC, the plumbing pipes. All sorts of things are made out of PVC. It's a relatively rigid polymer material. Here we're showing a blood bag that's used, and the tubing here, the neoprene tubing and stuff that if you've worked in the clinic or you've seen these type of materials. I'm not sure if we call that a consumer product. You don't buy that at the grocery store. But a lot of these biopolymers are biocompatible that are used in the clinic and in operations. PVC is one of them there. Polypropylene, and I've brought some examples to remind you of this type of stuff. Syringes and other type of tubing materials. They're a little bit more rigid materials. Then we have polytetrafluoroethylene, or PFE. It's Teflon is the common name for it. Teflon is neither hydrophilic nor hydrophobic. It repels everything, actually. Most polymers are hydrophobic. They'll be lipophilic. They'll have an affinity for nonpolar materials, but they'll not want to interact with water. So water will usually bead up on the surfaces of polymers. But we can make hydrophilic types of polymers. Polyvinyl alcohol, for example, is useful for a number of things. So this is just a few that we're going to get into now. Let's go to the board and talk about these. And I like to introduce this discussion of polymers talking about the initiation here again with peroxide. And radical polymerization of alkenes is just one process now. It was the first one, so it fits in, I think, to chapter 15 here. So what if we leave out the reagent here and we're just adding the peroxide, but no other reagent? Okay. What can occur here? Well, we can still have the initiation going on. Okay. There's no HBr in here now. There's no NBS. There's nothing else in there except the alkene. Okay. What can occur? Let me draw this on the other side here. Okay. Well, you can take the oxygen radical and add it to the alkene. Okay. Well, what does that give us? Well, it gives us an ether, right? It makes a carbon-oxygen bond. Okay, so we're doing an addition, just like bromine did an addition before. Before, when we had HBr there, we had a hydrogen atom source with oxygen. It has a high affinity for the hydrogen off HBr. But now we don't have any other reagent in there. What else can occur? Well, oxygen itself can add. Okay. Well, okay, that's reversible. That could go back or whatever. But what else could occur here? Well, you've got more alkene, right? Just add it again. And what do you get? You get another carbon-carbon bond and another secondary radical. And the addition should go on the end, right? And you should get the more substitute radicals. So don't add t-butoxy radical to the internal position and get the primary radical. Okay, so I'm drawing it this way for a purpose. Notice we're always secondary here. And the next alkene goes on there in that way. Well, what else can occur now? Well, more alkene can go on there. And what are we going to get? Well, I think you can see the idea here. We're going to get more of this to occur. And can it go again? It sure can. Okay. In fact, it can go hundreds of times or even thousands of times, depending on the conditions and how this is run, and depending on how the termination might occur. Okay. So let's see. Let's add one more and talk about the termination steps that might occur. Oh, we're getting a lot of them on there, aren't we? I think we've put 4 on there. We've made a lot of carbon-carbon bonds. And what can occur at this time? Well, it can terminate. If we have, a tiny amount of the terbutyl peroxide, we're going to have a tiny amount of this relative to the amounts of alkene in there. So usually, we start out with a lot of alkene. But as that's consumed, eventually all we have is the way to terminate here is to combine those. Remember I said radical-radical couplings are very rare. So this step's much slower than adding to more alkene. Well, what you get then is this. And let's see, we'll just generalize this now. We'll just say, okay, that there, and we'll say X there, okay. So we're drawing the initiator on the ends here, and indeed that's often the case. And then here's where our alkenes were, right? Right there, 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 there. Oh, maybe I didn't draw that one right. Let's get that one drawn correctly. Oh, there we go. Okay. So there we got the alkene monomer units that we can see here. And that's the terminology. This is called the monomer. Not a very creative term, is it? Mono meaning the single unit out of what? The polymer now. Okay. And the polymer on the ends does have the initiators there, but oftentimes we just draw it like this. So from propene there, we just draw it like this. And we don't need to draw 4 or 5 or whatever specified number of units. So we'll just leave the ends undefined. That's okay. And then as long as we show the monomer units correctly coming together. And notice with propene here, you have this methyl group here, right? And these methyl groups alternate 1,3 to each other. The methyl groups, okay? And the background, the backbone of the polymer, you could say, is all carbon-carbon bonds, okay? So this is actually polyethylene, or PE. It's this material right here. It's the top of this drink bottle here. It's kind of a softer material than polyethylene. See, polyethylene is this stuff right here, which is a little more rigid. And we'll do polystyrene also. And we got low density polyethylene here. So these are just a few things. Polystyrene we normally see as styrofoam, which is polymerized or molded with air blown into it. So it's a little more diffuse and lighter. But this is a solid block in a prism. It has optical properties like glass, actually. This is polystyrene. But these other materials are a little bit different there. There's polyethylene, polypropylene, and polyethylene, which is blown into a bag, right? Really, really thin material. And these dyes are added to them. Normally the polymers themselves are white or clear in their appearance or opaque, and you have to add a dye, a colored material. It depends on how they're processed at this point. This is now a solid material. Propene itself is a gas, actually. Not all the monomers are gases that way. When it's polymerized, it becomes a solid material, okay? And you can remelt that down, and you can do extrusion molding, or you can draw it into fibers. Very versatile material. Can be recycled and done into a number of things. Let's look at a couple other polymers here. So if we just have ethylene itself, what polymer is that going to look like? Well, it'll just be the straight chain, right? 1, 2, 3. Yep, there are 4 units there. It's just straight chain. And maybe you've heard about this high density polyethylene. versus low density polyethylene. Most radical polymerization of ethylene will give low density polyethylene, and that means it's not isomorphous. It's not all the same chain length. And plus, sometimes you have branching that can occur in the radical process. If there's branching or if these are short, then it's low density polyethylene. If it's high density polyethylene, these are very long chains and they're organized in such a way that you can make very strong fibers. In fact, a lot of ballistic materials, bulletproof vests in military grade polymers are actually high density polyethylene now. That can stop bullets. This material, HDPE, is actually stronger than steel weight for weight. Okay, if it's organized correctly and if it's monodisperse, if it's all the same length. Don't worry about that. For the purpose of our class, you need to connect the type of monomer to the type of polymer structure-wise and seeing it. Make sure if you have a group on the alkene, you have it 1,3 to each other. Let's look at a couple other examples of this one. How about this one? What's this material called? Vinyl benzene? Well, it has another term for it, styrene. Styrene is the common name for vinyl benzene. And polystyrene looks like this if you polymerize it. Well, I'll just draw 3 here. You have the phenyl groups left behind on the chain. Okay? So there's each monomer right there. And don't worry about how it terminates. Usually it has it on there. Sometimes it could terminate by doing a beta elimination and put an alkene on the end. There are ways to do that too. There are other ways to polymerize alkenes also with organometallic catalysts, Ziegler-Natta catalysts, which give organized or isotactic type of materials. These are stereocenters actually. Okay. You can have them all on the same face or alternating, or you can have them random. We're not going to get into that, but that changes the properties here. But with this one here, that's polystyrene or PS. Okay, that has the phenyl groups on there. And in a solid state, it's actually very rigid material. Like I said, you can polymerize it in the presence of air or a gas and make styrofoam, which is very light material. All of these are less dense than water. They'll float on the top of water. They can be recycled, of course, or left in a landfill. Some of them last up to 1,000 years in the landfill. We don't actually know how long they'll persist in the environment. They don't degrade, okay, microorganisms. Oh, no, there are some microorganisms that actually do digest polymers, but that can be a problem. They're actually victims of their own success because they're so robust and so cheap now. We throw a lot of them away, even though most municipalities now have very good recycling processes. Most people don't take advantage of that, but yeah, can be a problem there. But yeah, polystyrene. So for our class, notice the difference between polyethylene versus polystyrene. One more here. How about vinyl chloride, PVC? And, from plumbing pipes, if you've worked with that, or PVC materials, PVC's in everything from car parts to screwdriver handles to toothbrushes, plumbing devices. These things are all over the place. It used to be thought that any moving part in a machine or a car had to be a metal-based material. No, that's not the case now. We have polymers, polynylon, high-density polyethylene that are very robust, very mechanically sound, and you can use them in all sorts of applications, which is amazing stuff. Well, it's polyvinyl chloride. Well, it's ethylene, but with a chloride on there. So when you polymerize it, it looks like this, right? You got the same backbone here for polyethylene. And then just put the alternating chlorides on there, okay? And the X, what does the X mean? It means this chain is repeated hundreds or thousands of units. And make sure they're 1,3 to each other. You can go through the polymerization process again, the mechanism, the radical adding on the end, and then you get the radical intermediate here, right? Which looks like this. Oh, there it is. Okay, which is a secondary radical, not a primary. If you added the radical here, you get a primary radical, right? And then this polymerizes with more, right, to give this product. And I think that's it. I think that's all we'll be able to do. But we can ask questions in different ways. We can show you a polymer and ask you what monomer it came from. okay? Or we can show you a monomer and ask you what polymer it would form, okay? And we can ask you a little bit about the mechanism too. So there's a couple things to be aware of there. We're not getting into all the material applications and everything like that. Those are a little bit beyond. There is the one thing though. I started out with the dental application of polymers, right? And what was that? Well, that was to catch your attention there because some of you want to become dentists. And what was the monomer there? Well, it was this cyanoester. Actually, there's a lot of these, cyano, yep, triple bond to carbon. There's a lot of these cyanoacrylates, they're called. And depending on what's here, I think if this is a butyl group, if it's a butyl ester cyanoacrylate, that's super glue. You've played around with super glue, right? It comes in a little tube. You squeeze it out. Well, the initiator in that case is actually oxygen. This is a very reactive monomer because it's got the cyanide and the ester, which are both electron withdrawing groups. So even O2, the radical here, can add there and start polymerizing. Okay. The one that you use in the dental chair for the initiator is what? The camphor diketone. And that looks like that. Now this will form a radical in the presence of blue light, blue LED light. And what wavelength is that? Oh, it's 350 nanometer light. Okay, which is a little bit outside the visible range, and so that's a little bit higher energy. So the lower the wavelength, the higher the energy, right? It means the higher frequency. So that's what's actually coming out of the blue gun to initiate this. And what does the radical look like? Well, you can excite this to this. You can just push the electrons to that, right? Put the double bond between the two carbons and then you unpair the electrons here. That's considered the excited state, which can be populated in the presence of blue light. And then what? Well, look, you're off to the races, right? That can add here and give you the polymer, which will look like this. Now the initiator's stuck on the end there. And just draw the polyethylene backbone, that's fine. And then each carbon here is where the other groups are. And that looks kind of funny, but that's the one monomer, right? This is the two carbons of the alkene that are reacting. And then you create a tertiary radical here, right? Your intermediate. I'll let you go through that. Tertiary radical intermediate will be right there. It'll add to another monomer, which will give you this. And I keep trying chloride, sorry. Ester. And another one here. Yep. Look at that. So how many monomer units did we depict here? I think there's 1, 3, 4. Yeah. And X means there's hundreds of these long. You see forming this solid polymer material now, this acrylate thing. The onlay material for a tooth has some ceramic material in it. This matrix initially is a liquid here, which can flow, can get in the gap, the cavity, whatever, or connect the crown. And then the gun is put over the tooth, right? And this light can penetrate through that material. That's another advantage of this blue light. And a tiny amount of that is in with the liquid to begin with. But it only starts the polymerization when the blue light's added, okay? So it's a strategy for an application here. And these have the right properties to interact with the ceramic material. They're a little more polar and gives a better adhesive effect. Anyway, I think that wraps up that nicely for that topic. And we're about out of time, so